All right, everybody, welcome back here. If I'm here, it's gotta be maybe a quick video. Hopefully, what we can tackle today, a little covalent bonding. Why not? Well, we did some ionic bonding in a previous video. If you didn't watch that, I'll put a little link there for you to find it. But in covalent bonding, it's all about nonmetals. And basically, it's two nonmetals together. And when we get two nonmetals together, what happens is because of those periodic trends, frankly, neither one of them wants to give away their electrons. So unlike in ionic bonding that we talked about, where we have a metal and a non-metal coming together, and when those two get together, boom, off we go with the electron. We get that electron transfer, we get some ions being formed, and electrostatic attraction. Here, the best we could hope for is a little sharing of electrons. And that is the major difference between ionic bonding and covalent bonding. Covalent bonding is sharing of electrons. Ionic bonding, we get a transfer of electrons, ions being formed, no sharing of electrons happening there. So how does this sharing work? Well, if we just take a simple example, hydrogen has one valence electron. And if we took another hydrogen, one valence electron, since they're both hydrogen, clearly neither one of them is going to give away their electron to each other. So they're just going to agree, hey, let's do a little sharing here. And they will actually share those electrons. Now the two electrons there will count for the hydrogen on the left, giving that guy two electrons. Two electrons will count for the hydrogen on the right, giving that guy two electrons. And you know what? For hydrogen, that's perfect. Because if you look on the periodic table, there it is. Noble gas right after hydrogen is number 2, which is helium. So hydrogen is perfectly happy this way. It is sometimes referred to as a duet rule. It actually only needs 2 electrons. And that is something to remember. Hydrogen pretty much should only look like this. Pretty much 2 electrons. That is a single bond I drew there. By the way, that bond that we see up here can be represented with a line. One line represents 2 electrons or a pair of electrons, and that is a single bond. 2 lines represents 4 total electrons or 2 pairs of electrons. That is a double bond. And 3 lines represents 6 total electrons, 3 pairs of electrons. That is a triple bond. This bond is held together because, frankly, those electrons between them, there's some attraction to this nucleus, there's some attraction to this nucleus that essentially locks them into place and makes that bond in this case. This right here is what is known as a covalent bond. It's also known as a nonpolar covalent bond. Most people would just call it a nonpolar bond. A lot of people leave the covalent part out, but a nonpolar covalent bond it is. And pretty much this type of sharing is what is known as equal sharing of those electrons. So when you have equal sharing electrons, that is a nonpolar bond. We would expect these electrons to be shared perfectly equally with these guys, as like you think of it like a string, hydrogen on one end pulling the string, hydrogen on the other end pulling the string. They're not going to go anywhere if they're kind of doing a tug of war, so those electrons are going to be shared equally between them. A nonpolar bond, you could kind of think of it as a neutral bond. There is no positive side of that bond, there's no negative side of that bond. Because of the equal sharing of electrons, it's kind of like a neutral bond. So what happens when we don't have that type of bonding? Well, if we swap out that hydrogen for a fluorine, in this case, we will get this type of bond here. And again, hydrogen has 1 valence electron. Fluorine has 7 valence electrons, as is group number 7. Once again, hydrogen and fluorine, both nonmetals, both going to want to hang on to their electrons. We're going to get that sharing occurring. What happens in this case? Well, fluorine gets the 8 electrons, with the sharing of those electrons with hydrogen. Hydrogen gets the 2. Boom. Hydrogen again gets that duet rule and gets to 2 electrons and is very happy. And looky there, fluorine gets to 8, which is sometimes referred to as the octet rule. The octet rule basically means in bonding, especially covalent bonding, everybody will continue to make bonds until they have 8 valence electrons around them, except for hydrogen, it should only have 2. Why is that important? A little bit of what we talked about in ionic bonding. 8 is on the periodic table, the noble gases, right? And again, that is the purpose of all bonding. Ionic bonding, they're able to get to the noble gas configuration by losing and gaining electrons. In covalent bonding, they're actually able to get there by sharing electrons. So covalent bonding, ionic bonding, purpose, right there on the periodic table, everybody to become very much stable or make a stable situation like the noble gases. Remember, noble gases are chemically inert. They're extremely stable. And again, a reminder that these guys are not becoming noble gases. Again, they're not changing protons or anything like that. They are becoming like the noble gases with their electron configuration. So this type of bond, though, is not going to be shared equally. And that's because hydrogen and fluorine have what's different about them. They have different electronegativities. And electronegativity is the ability of an atom to bring electrons towards itself. And when you look at the periodic table, it increases as you go up and to the right and decreases as you go down. There it is. Fluorine, as far up and to the right as you could go without hitting a noble gas. Most electronegative element. Yeah. So with that being said, when we look at this bond, we are going to expect the electrons not to be shared equally, because in this case, if you think about the tug-of-war example, fluorine is going to be pulling on that rope a lot stronger than hydrogen is. And what that's going to do is essentially for fluorine, it's going to move all the electrons. If my highlighting here is all that electron density, all the electron density is going to end up over there by the fluorine, because it's going to bring it towards itself a lot more than the hydrogen. Let's have a little bit over there by the hydrogen. And the result of that is, unlike a nonpolar covalent bond, we're now going to end up with a bond that actually does have some charge difference. The fluorine is going to be what is referred to as being partially negative. That's a delta negative sign. It's going to become partially negative because the electrons are hanging out there. And the hydrogen, which is kind of like losing the electrons in this tug-of-war battle, is going to become partially positive. On the hydrogen side, this could also be represented with an arrow, which is sometimes referred to as a dipole arrow, where the arrow points to the side that's more negative in the bond. In this case, it would point towards fluorine. And the back part of this arrow that makes almost like a plus sign, you can almost see a plus sign there. This actually points to the more positive sign of the bond, or positive side of the bond, which is the hydrogen in this case. Now you may be asking, why are they partially positive and partially negative rather than full positive and full negative? The idea here is it's a covalent bond, which means even though they're not sharing equally, there is still some aspect of sharing. And that is different than an ionic bond that we talked about in that previous video, where you're going to get that electron transferred completely from the metal to the non-metal. And the result of that in an ionic bond is you get a full positive charge cation, a full negative charge anion. But here, there is still some aspect of sharing happening. So that's why it is only a partially positive and partially negative charge. This type of bond right here is another type of covalent bond. This is what is referred to as a polar covalent bond. Or again, most people will just call it a polar bond and kind of leave the covalent out of it. So a polar bond is unequal sharing of electrons. So we have a nonpolar bond, which is equal sharing of electrons and kind of makes a neutral bond. We have a polar covalent bond, which is sharing of electrons, but unequal sharing of electrons, creating this kind of charged bond where you could draw this arrow. And once again, this arrow here is sometimes referred to as a dipole arrow or a bond dipole arrow. So if you think about the three types of bonding, we have ionic bonding, transfer of electrons, polar bonding, unequal sharing of electrons, and nonpolar bonding, equal sharing of electrons. So on one end of the stream, we have ionic bonding, which no sharing, a transfer of electrons. Other end, we have a nonpolar bond, which is covalent and equal sharing of electrons. And in the middle, we have a polar bond, also covalent, also two nonmetals, and this is unequal sharing. So not so unequal sharing that they transfer the electrons, but not equal sharing, kind of in the middle. So that is kind of the three areas of bonding that we have. All three of these all allow everybody to achieve noble gas configuration, which is really the whole point of bonding. So how do we know if we're going to get one of those three types of bonds? You can actually use electronegativity values to help you decide that. And these are some of the electronegativity values you can get from a periodic table, are based off of the periodic table and their location. And you can actually use this to figure out what is referred to as bond polarity. And bond polarity is simply between two atoms within a bond. Is it going to be an ionic bond? They're going to transfer electrons. Is it going to be a nonpolar bond where they will share electrons? Or is it going to be a polar bond where they're going to share electrons unequally? So how do we do this? We sometimes calculate what's sometimes referred to as delta En, and that is the change in electronegativity. And basically all you do is go to this table and take the two electronegativity values for those elements involved and just subtract them. Take the larger number from the smaller so you get a positive number. Let's take our hydrogen, for example, bond. Go here, hydrogen 2.1, 2.1 for electronegativity value for that, 2.1. This, by the way, is the Pauling scale. It goes from 0 to 4. 4 is the most electronegative. 0, not so much there. Not so much electronegativity. So clearly here, if we take a difference in electronegativity, that is 2.1 minus 2.1, that is a difference of 0. And when you look at difference in electronegativity values, anywhere from 0 to about 0.4 is considered a nonpolar bond. Anywhere in a difference in electronegativity from like 0.5 to below 2 is considered a polar bond. And usually anywhere in an electronegativity difference of approximately 2, that's ionic. I'll tell you the truth, you don't really need electronegativity values for ionic because all you need to know is metal, non-metal, it's ionic. That's a pretty safe bet. So I wouldn't even worry about electronegativity values for ionic bonding. I would worry about it more for covalent bonding here, whether it's nonpolar or polar. This is the difference of 0, falls in the nonpolar, and this would be a nonpolar bond. By the way, this difference of 0 that you get is also sometimes referred to as a pure covalent bond. And that is still a nonpolar bond, but it's like as perfect equal sharing of electrons as you could get. So sometimes books will classify it as a pure covalent bond, and that's when you get a difference in electronegativity of 0. Now, if I take something like carbon and hydrogen, and I look at carbon up there on our chart there, and carbon is a 2.5, right about there, and our hydrogen is 2.1. Take the difference in electronegativity value, that is 2.5 minus 2.1. That's a 0.4 difference. That is my high end here, and this is a nonpolar bond, which basically means equal sharing of electrons. Reason for that cutoff is carbon hydrogen is pretty much what you find in a lot of organic compounds, which are nonpolar. That's maybe why the cutoff's right there at 0.4. But there is kind of a difference, right? This is like perfect equal sharing of electrons. Here is a perfect equal sharing of electrons, and not so much. There's a slight difference, but not enough to be considered polar in this case. So this is still a nonpolar bond. Let's take a look at maybe HF that we saw earlier. So hydrogen again, 2.1. Fluorine is the most electronegative you can have, which is 4. Difference in electronegativity, 4 minus 2.1. Once again, just take the larger number minus the smaller number. Give me 1.9. That is definitely below 2, barely, and above 0.5. So this is definitely a polar bond. Again, we could draw that bond dipole arrow pointing to the one that is more electronegative. Let's say we had nitrogen and oxygen bond. We look at nitrogen here to find the value, which is 3. We take a look at oxygen, which on this list is right there, 3.5. Difference in electronegativity is 3.5 minus 3 gives us 0.5. That is right here, and that is a polar bond, this guy. In this case, our arrow should point towards the oxygen as it is more electronegative in this case. Now, change page here, fresh page. Let's take a look at sulfur and oxygen, for example. Sulfur here on the chart, 2.5, and oxygen, which is the one we just did, 3.5. And once again, we take difference in electronegativity. That's going to be 3.5 minus 2.5. And that's going to give us a difference of 1, which is between 0.5 and less than 2. And that would tell us it is polar as well. Remember that cutoff there is 0.5 to 2, or less than 2 is polar. And again, pretty much 0 to 0.4 is nonpolar. Again, we should draw the arrow going in this direction here. Now let's say we took a bond between nitrogen and chlorine. Nitrogen is 3. Chlorine is right there. It is 3 as well. Look at that. Change in electronegativity. Probably could get the calculator, but might not need it. It is going to be a 0 in this case. That is right here. That's going to be a nonpolar bond. By the way, in a nonpolar bond, sharing equally of electrons, you do not draw that dipole arrow. So the dipole arrow here is only for polar bonds. You should draw that. That's a nonpolar bond. And you're saying, well, that's different elements. And that is true. They are different elements. So there are some trends on the periodic table that could really help you when you're trying to decide these things. So for example, you look at the location of nitrogen, roughly there. And you look at the location of chlorine, which is below it and to the right. They're what are referred to as diagonal relationship, kind of down and over one. So nitrogen is further up, but chlorine is further to the right. They actually counteract their differences there in electronegativity and end up being 0. There's a few places that you'll see that on the periodic table. Nitrogen chlorine is an example of that. Carbon and sulfur as well. So carbon is 2.5 and sulfur is 2.5. Also diagonal of each other. Here is carbon and sulfur, diagonal of each other. So they will actually cancel each other out in terms of electronegativity and give you a non-polar bond. So it's definitely possible to have two different elements based on their location on the periodic table. They're diagonal of each other, could have the same electronegativity value. Now, do you always need these numbers to make an educated guess? No, you don't actually. So if you take a look at a couple other examples here, just to wrap it up that we were talking about, you looked at the nitrogen oxygen example. They are in the same period on the periodic table. Oxygen's further to the right, so this combination will give you a polar bond. So if you're comparing two things in the same period on the periodic table, and they're in the same period, good chance it will then give you a polar bond. One further to the right will get the arrow pointed towards it, as it is more electronegative in that case. We also looked at sulfur and oxygen, which happens to be in the same group on the periodic table, and oxygen's further up in the group, making it more electronegative, also going to yield you a polar bond where it will point to it. So if you're just comparing something in the same group or something in the same period on the periodic table in terms of electronegativity, you really don't need the chart. One further to the right in the same period, one further up in the same group will be more electronegative and probably will yield you a polar bond. If you have two elements that are the same in a bond, it will get you a non-polar bond. If you have some diagonal relationship on the periodic table, you'll get yourself a non-polar bond as well. Well, these are some quick ways you can figure out the type of covalent bonding. I hope this helped. Anything else you want to know about, let me know, and we'll probably get a video out there for it. Otherwise, we'll see you on the next one. Bye-bye.